All right, now the graph of our logarithmic functions, you're going to see that those are the inverses of our exponential functions. So notice that the properties of the inverses that we discussed back in 4.1 are going to hold. If we've got an increasing exponential function, y equals b to the x there in blue, then its inverse function is going to be y equals the log of x with base b, where b is greater than 1. And remember, a function and its inverse are symmetric about the line y equals x. And again, the x's and y's are swapped around. What was the domain of an exponential function is now the range of a logarithmic function. And what was the range of the blue exponential function is now the domain of the pink logarithmic function. Interesting. Okay? Now, here's an example again, but this time our exponential function is a decreasing exponential function here in blue because that base is in between 0 and 1. And so its inverse, symmetric about that line y equals x, okay, is going to look a little something like that pink one. It's going to be a decreasing logarithmic function. Again, domains and ranges are swapped around from a function to its inverse. All right, now, to actually graph these functions, let me show you how to do this. To graph these functions like 66, I don't think I'm gonna graph y equals 5 to the x. No. What I'm going to do is I'm going to rewrite this logarithmic equation in exponent form. Remember, it's 5, the base of 5, raised to the y, equals the argument x. That is its equivalent exponent form. And so, just like I graphed exponential functions in the last section, I'm going to graph this exponential relationship, x, y ordered pairs. But y'all, instead of picking out values of x, okay, see where I would be putting those in for x over there? No, thank you. I think what we should do, I wanted to slide all of those over. Oh, shoot. Maybe I'll slide that little bar over. Ha, 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 ha. You think you're going to. Okay. Move each individual little piece of it over. There we go. Now I'm going to pick out values of y. Now those go up in here for the exponent, in the exponent position, right? They're going to go in there for y, and then that's going to give me the x value that corresponds. Okay? X is equal to 5 to the y. So when y is -2, 5 to the -2 will give us the x value. 5 to the -2 is the same thing as 1 over 5 squared. So 1/25. 1 over 25. Can y'all read that okay? Kind of got scrunched over there. There we go. 1/25. When y is a -1, x is equal to 5 to the -1st. That's the same thing as 1 over 5 to the +1st, or just 1/5. Okay? When y is 0, x is 5 to the 0, which is 1. Okay? When y is 1, 5 to the 1st is our x value, or just 5. And when y is 2, 5 squared gives us 25. So let's plot those points. Okay? When x is 1/25th, which is like 0.04, I think, just little bitty, y is down there at -2. So I'm going to scooch that really close over there to 0, but not 0. Okay? I'm going to plot the next ordered pair, 1/5 for x, -1 for y. 1/5 for x, -1 for y, about right in there. We got to do the best we can there. All right. 1/0 is here. 5/1 here. And then I'll keep in mind 25, 2. I will take off and head to that value of 25, 2, right? 25 for x, 2 for y. Now, what's going to happen along here is now the y-axis serves as a vertical asymptote. It's totally swapped around from the exponential functions because logarithmic functions are the inverses. Okay? Back in exponential functions, the x-axis served as a horizontal asymptote. Now this y-axis is serving as a vertical asymptote. Total swappage, right? The equation that we just graphed was y is equal to the log of x with base 5. Okay? Let's do 68. This is y equals the log of x with base 1/5. Again, rewrite this in its equivalent exponent form. The base raised to the exponent of y is going to give us our x values. That's how I'm going to crunch my xy ordered pairs. Okay? So I'm going to make a little chart of xy ordered pairs. But what I want to do, instead of picking out values for x over here, I'm going to pick out values of y. Let's do those same -2, -1, 0, 1, and 2. And then let's find the corresponding x values. I think I'm going to scroll up here a little bit and I'll be able to do all that chicken scratch up here. So my first x value, when y is -2, x is going to be equal to 1/5 to the -2nd. Hey, y'all, remember, fraction raised to a negative is the same thing as the reciprocal of that fraction, now raised to a positive. Yeah. 5 squared, I know that. 25. Right? What about when y is -1? Our equation says x is equal to 1/5 to the -1st, which is the same thing as 5 over 1 to the +1st. That's just a fancy way to write 5, isn't it? 5 to the 1st. 5. All right, what about when y is 0? When y is 0, x is equal to 1/5 to the 0. Anything to the 0 power is 1. What about when y is 1? Let me just edit that. 1/5 to the 1st is just 1/5. And what about when y is 2? 1/5 squared is 1 over 25. Square the top, square the bottom. Let's plot those points. X is 25, y is -2. Okay, that's totally not on my graph paper. But 5, -1 is on my graph paper. I like it. 1, 0, I like it. 1/5, +1, about there maybe. And 1/25, 0.04, 2. Okay. All right, you see the little swoopy shape? Treat that y-axis as a vertical asymptote and draw a nice little smooth curve through all these points. I'm going to head toward 25, -2. Here we graphed y equals the log of x with base 1/5. All right, so then, is it on the next page? No, it's just down below. Down below on your notes, it says, based on the graphs in example 7 and our knowledge of exponential functions, we're going to offer the following summary of the characteristics of logarithmic and exponential functions. Check them out. Exponential functions are of the form y equals b to the x. If the base is greater than 1, you've got the increasing exponential function, okay? If the base is in between 0 and 1, you've got the decreasing exponential function. The domain, oh, I wish we could get all that on there. Oh, that'll be good enough. The domain is all reals. The range is positives. Horizontal asymptote, the x-axis. Passes through the point 0, 1. Okay, if the base is greater than 1, the function's increasing, like in orange. If it's in between 0 and 1, the function is decreasing. What else is there? Nothing. Okay, good. Now, for logarithmic functions of the form y equals the log of x with base b, if the base is greater than 1, it's still an increasing function, but there's some stuff that swaps around, okay? Notice the domain, all the x values, if you read this from left to right, the domain is positives. That's the same thing as the range of its inverse. And the range of this thing from bottom to top, the range of this thing is all reals, swapped. These have vertical asymptotes at the y-axis. The vertical line x equals 0 is your y-axis. These pass through the point, swap 1, 0. But this is the same. Same z's right in here. Same. If b is greater than 1, the function is increasing. If b is in between 0 and 1, the function is decreasing, right? Like we got going on there in pink. So those are just some of the characteristics.